We are now in the 12th lecture of the series of lectures entitled Bracket Algebra. Let me touch the essentials of the previous lecture 11. Consider three kets. We denote them as ket psi 1, ket psi 2 and ket psi 3. And suppose these kets satisfy the relation which indicates that they are not orthonormalized, that is, they are not mutually orthogonal and they also are not normalized to unity. Starting from this set of ket vectors that are not orthonormalized, we can build a set of orthonormalized ket vectors through Graham-Schmidt orthonormalization procedure. In other words, we can construct three ket vectors, a ket phi 1, ket phi 2 and ket phi 3 with the help of ket psi 1, ket psi 2, ket psi 3 that satisfy the relation bra phi I ket phi j equal to Kronecker delta ij. Back to the present lecture. In lecture 4 of this series of lectures entitled Bracket Algebra, we discussed inner product or overlap that represents multiplication of a bra vector with a ket vector. We discussed its significance and showed how we can generate a scalar in general complex through the product of bra and ket. Can we multiply the other way around? We ended up lecture 11 with the question, can we multiply a ket with a bra? The answer is yes. We shall now discuss the product of a ket with a bra, and this is called outer product. Let us discuss it in details now. Product of a ket vector with a bra vector is called outer product. This makes possible the generation of a matrix using ket and bra. And one of the importance of matrix is that operators are represented by matrices. It follows thus that the outer product makes possible the generation of an operator using ket and bra. How is it possible? Let us see. Consider a ket vector, say ket A, equal to the column matrix having elements A1, A2. Clearly it is a 2 cross 1 matrix. Then what will bra A be? It is a row matrix, the elements being A1 star, A2 star, and it is a 1 into 2 matrix. We also consider another ket vector, ket B, which is equal to the column matrix B1, B2, which is a 2 cross 1 matrix, and so bra B will be a row matrix B1 star, B2 star. It is a 1 into 2 matrix. We take product of ket with bra now. First write ket A and then place bra B. Put their respective matrix formats. So it is equal to the column A1, A2, which is 2 cross 1 matrix, multiplied by the row B1 star, B2 star, which is a 1 cross 2 matrix. Clear that by the rule of multiplication of matrices, the two matrices 2 cross 1 and 1 cross 2 are compatible. And so matrix multiplication results in A1 B1 star, the first element of first row, A1 B2 star, the second element of first row, A2 B1 star, the first element of second row, and A2 B2 star, the second element of second row. We clearly end up with a matrix operator, which is a 2 cross 2 matrix. As it is an operator, we can designate it by a hat, say the hat symbol atop the letter A, indicating that we have ended up with an operator represented explicitly by a matrix. Have we got things right? Let us recheck taking another example. We take product of ket B with bra A. And what is ket B? As mentioned earlier, it is a column matrix B1, B2, a 2 cross 1 matrix. And what is bra A? We had for it A1 star, A2 star, a 1 cross 2 matrix. Can we compile ket B bra A? Let's try. write the respective matrices, and the 2 cross 1 matrix is compatible for multiplication with 1 cross 2 matrix. We now take the matrix product. The result is, this is a matrix operator, a 2 cross 2 matrix. Let us designate it as sum operator B hat, say. Clearly, with ket A equal to A1, A2, ket B equal to B1, B2, the product ket A bra B, which is the matrix, is not equal to the product ket B bra A, that essentially is the matrix. In other words, the matrices aren't equal. This non-commutativity is an important observation. Having defined outer product in clear terms, let us now involve ourselves in solving a couple of problems. Consider ket 1 to represent the column matrix 1, 0 and ket 2 represents the column matrix 0, 1. Find ket 1 bra 1, ket 1 bra 2, ket 2 bra 1, ket 2 bra 2 and find their sum. The answer, given ket 1, so bra 1 is the row 1, 0. Given ket 2, so bra 2 is the row 0, 1. Now ket 1 bra 1 will be the matrix multiplication of the column matrix 1, 0 with the row matrix 1, 0. That leads to a 2 cross 2 matrix 1, 0, 0, 0. Similarly, ket 1 bra 2 will be 0, 1, 0, 0. Ket 2 bra 1 will be 0, 0, 1, 0. And similarly, ket 2 bra 2 leads to the matrix 0, 0, 0, 1. Clearly, the sum is, let us add the matrices to get 1, 1 in the first row and 1, 1 in the second row too. This is the result. Next problem, a similar one but more calculations. Consider ket 1 to be the column 1, 0, 0, ket 2 is the column 0, 1, 0 and ket 3 stands for the column 0, 0, 1. The question is, find ket m bra n. Also find summation over the dummy indices m and n, ket m bra n. The answer is, ket 1 is, so bra 1 is the row 1, 0, 0. Ket 2 is, so bra 2 is the row 0, 1, 0. Ket 3 is, so bra 3 is the row 0, 0, 1. Then the ket m bra n values will be, ket 1 bra 1 is, put the column matrix 1, 0, 0 and the row matrix 1, 0, 0. Now take the product to get the 3 cross 3 matrix. We have 1 here and all other elements are 0. Next, ket 1 bra 2 is, now we get a 1 here and all other elements are 0. Ket 1 bra 3 is 0, 0, 1, 0, 0, 0, 0, 0, 0. Ket 2 bra 1 gives, ket 2 bra 2, we have 1 here at the second row second column and all other elements are 0. Ket 2 bra 3 is, ket 3 bra 1 is, ket 3 bra 2 and ket 3 bra 3. Having found all the ket m bra n values, we are now in a position to evaluate the sum. Let us write all the terms it reproduces. Clearly, the next step involves sum of all the matrices that we got, and it is a 3 cross 3 matrix with all elements unity. We thus have got the result. We end this lecture 12 with a question that would be taken up in the next lecture number 13, and it is, what is projection operator?